As we venture further into the enigmatic world of metamaterials, we find ourselves at the threshold of a technological revolution. In Part 1, we delved into the principles and complexities of creating these extraordinary materials, particularly in the realm of manipulating electromagnetic waves. The challenge of designing geometric patterns smaller than the wavelengths of visible light and near-infrared spectra becomes apparent. These heroes must operate on a scale that is incredibly minuscule compared to the dimensions of atoms. But as well discover, humanity's quest for miniaturization has made remarkable strides, bringing us closer to the manipulation of visible light. We'll dive into the intricacies of creating radio-based metamaterials, which served as a foundation for understanding the principles involved. These materials have opened up possibilities to mitigate the Doppler effect, revolutionizing communication in space and enhancing the performance of radio-based technology. That's just the beginning. We'll take you through a journey of contrasting scenarios, where conventional technology faces off against metamaterial-based advancements. Explore how metamaterials can redefine the experience of soldiers on the battlefield, offering enhanced invisibility communication and imaging capabilities. Designing geometric patterns smaller than the 390 to 700 nanometers of visible light over 750 to 400 nanometers of the near-infrared spectrum posed a significant challenge. The challenge arises from the fact that atoms are just 0.1 to 0.3 nanometers in size, which complicates the creation of elements since only a limited number of atoms can fit into such minuscule structures. To comparison, even human biological cells, which we consider small or typically thousands of nanometers in size, making them visible with a standard microscope. In contrast, cells within a metamaterial must be hundreds of nanometers or smaller. In recent decades, we have made remarkable strides in miniaturization. For instance, transistors in modern processors are about 14 nanometers in size, which is approximately 50 times smaller than an earliest wavelength of visible light, deep red, and the cusp of the ultraviolet spectrum. So we are approaching the size range required for manipulating visible light. However, working at these scales presents challenges due to the limited material available before we reach the wavelength size of the light we aim to manipulate. Metamaterials operating in the visible infrared spectra are indeed possible, but creating them is considerably more complex. Typically, they consist of extremely thin layers of two very different materials, where the combinations of these layers are significantly thinner than the wavelength of optical light. Radio-based metamaterials are the ones we understand best, as they were the first to be developed. Most natural materials have positive values for both permeability and permittivity. Some exceptions include ferrites, which have positive permittivity and negative permeability, and plasmas, which exhibit negative permittivity and positive permeability. Metals behave like a plasma above their plasma frequency. But it's important to note that metals possess this property only at frequencies beyond the optical range. Now let's delve into the process of creating radio-based metamaterials, as they serve as an excellent foundation for understanding the principles involved. When we approach the plasma frequency in metals, they transition from being effective conductors to poor ones, and they struggle to excite currents properly. This phenomenon results in waves passing through the metal, as if it were within a quasi vacuum, rather than a solid substance. By creating very small metal rods, we can prompt them to mimic the behavior of a plasma, thus achieving negative permittivity within a specific wavelength range. Similarly, crafting small ferrite rings allows us to attain negative permeability for a designated wavelength range. However, these materials, when used individually, do not produce the coveted negative refraction. The true magic emerges when we combine these rods and rings to form a metamaterial element. The amalgamation of these components results in a metamaterial with both negative permeability or negative permittivity, consequently yielding a negative refractive index. It's important to note that rods and rings in isolation cannot generate the desired negative refraction. The synergy between these elements is essential to achieve the desired effect. With our first metamaterial in hand, we can now explore its potential applications. Suppose you wish to focus a beam of radio waves on a receiver. Using a conventional material as a focusing lens would lead to further dispersion of the radio waves. In contrast, a layer of our metamaterial exhibits the opposite behavior. Remarkably, this material can be designed in a flat configuration and still efficiently concentrate the waves onto the receiver, making it particularly suitable for electronic applications. This achievement represents the realization of a perfect lens, capable of focusing radiation without the need for variations in the lens thickness. Further miniaturization of this setup extends its applicability to shorter wavelengths. Additionally, we can fine-tune the properties of the metamaterial to act as a perfect lens only for specific frequency ranges. For example, we could optimize it for the 2.4 GHz frequency, corresponding to a 12.5 centimeter wavelength, commonly used in Wi-Fi communication. By doing so, we enhance signal quality, efficiency, and signal-to-noise ratios, resulting in improved Wi-Fi performance. Another intriguing effect we can harness is the reverse Doppler effect. Altering geometry of the metamaterial elements, we can compensate for Doppler shifts. The Doppler effect is a well-known one encountered in a vehicle with a horn, where siren approaches or moves away from the observer. As the vehicle approaches, the pitch of the sound rises, a phenomenon known as blue shifting. Conversely, as it recedes, the pitch lowers, referred to as red shifting. This effect is familiar in astronomy, where stars experience blue shifts when approaching and red shifts when receding due to the expansion of the universe. In the context of fast-moving spacecraft, the Doppler effect poses a challenge. Signals transmitted through space experience Doppler shifts as the relative positions of the transmitter and receiver change. These shifts result in blue or red shifts based on whether the objects are approaching and longer away from each other. NASA has grappled with the challenge of compensating for these shifts, often requiring expensive equipment to counteract their effects. An illustrative instance of this issue occurred during the Virgin spacecraft's descent into the atmosphere of Saturn's moon, Titan, which was accompanied by the mothership, Cassini. Due to a Doppler issue, the deployment of the Huygens probe was delayed by years, nearly resulting in a loss of data. Metamaterials offer the exciting prospect of mitigating the Doppler effect, enabling the receiver to capture the exact frequency it was designed to receive. This advancement holds significant benefits for spacecraft, making radios more reliable, lightweight, and energy efficient. Another remarkable attribute of metamaterials is their capacity to perfectly refract radio waves from various angles onto the receiver, eliminating the need to adjust the receiver's position for optimal signal reception. Let's delve into a real-world scenario to showcase the practical implications of metamaterials, especially within military contexts. Consider two soldiers, Romulus and Remus. Romulus relies on conventional technology on the battlefield, while Remus employs metamaterial-based tech. How do their experiences differ? Romulus employs camouflage gear and face paint to reduce his visibility to the enemy. Unfortunately, this doesn't conceal his infrared signature. He remains far from invisible. Moreover, the process of camouflaging his gear and applying face paint consumes valuable time. As Romulus' unit advances on the battlefield, they struggle to pinpoint the locations of other units or even the positions of their fellow team members. This lack of situational awareness can lead to friendly fire incidents, a significant risk when troops cannot identify one another. After a grueling day on the battlefield, Romulus and his unit take a much-needed break. However, Romulus' electronic equipment relies on bokeh batteries due to its high power consumption. Setting up solar panels to recharge the equipment and establishing a satellite uplink for further orders proved to be time-consuming endeavors. Aligning the uplink accurately with the satellite overhead is a hit-or-miss process. After considerable effort, he manages to establish contact with his superiors for updated orders. while the communication gear employs encryption to prevent eavesdropping by the enemy. This added security comes at the cost of increased power demands and slower transmissions. Because of the added encryption layer, Rombolus is concerned that his batteries may not last or that his communication gear will take too long to send and receive messages to be practical. Despite the continuous operation of the side panels while he set up his equipment, but then he becomes apprehensive about whether there's enough charge left to complete the mission. Their orders are to scout a nearby enemy encampment and relay back images. They approach stealthily, hoping to avoid detection. Rombolus carefully utilizes his camera to capture images of the enemy camp, zooming in areas of potential interest. However, the zoom capability of his camera lens is limited. His higher resolution demands bulkier and heavier lenses. This operation takes place at night to avoid enemy lookouts and snipers, compounding the problem because the night vision capabilities of the lenses and camera are limited. Consequently, he must get perilously close to the encampment views for images. The day takes a turn for the worse when Rumbo's squad is spotted, and they must make a hurried retreat into enemy fire. It takes several hours before he can establish an opening to his superiors and provide them with the required footage. Murphy's Law, which states that anything that can go wrong will go wrong, particularly applies to both electronic equipment and the battlefield. In line with this law, the batteries deplete before the images can be uploaded, forcing Rombolus to describe the situation to the superiors over the radio and hope that his account contains enough detail for them to make use of the information. In contrast, Senna's experiences a much more favorable day. He wears a Metamaterial infrared armor suit that directs his heat away from him, rendering him invisible to infrared night scopes. He also dons the latest chameleon suit composed of Metamaterials that bend light around him, making him virtually invisible in the visible spectrum during the day. Unlike movie portrayals, these metamaterials are robust and energy efficient. The metamaterial-based radio transmitters provide pinpoint location information for his unit on the battlefield, ensuring that he always knows the positions of his fellow soldiers and minimizing the risk of friendly fire. Although it was a long day's trek, Simmer's equipment is relatively lightweight, thanks to the metamaterials they incorporate. Furthermore, this equipment consumes less power due to its enhanced efficiency, allowing for the use of smaller batteries. Summers can quickly and completely recharge his equipment, ensuring that it remains well-equipped and ready for the challenges of the battlefield. Summers' equipment includes Metamaterial solar panels that are significantly lighter and more efficient than the ones Rombolus had been carrying. The metamaterial transmitters enable him to establish connections rapidly and maintain direct communication with his superiors throughout his mission. The ultra-compact and efficient metamaterial electromaterial processes demand minimal power for real-time encryption and decryption of communications. This technological advance highlights the role energy consumption plays in computing and the resulting heat generation. Summers benefits from reduced exposure as his metamaterial equipment conceals him better than traditional electronic devices, which tends to stand out on thermal zone infrared detectors. Like Rombolus, Summers receives orders to scout a nearby enemy encampment and capture images for analysis. He uses his metamaterial camera, equipped with an exceptional zoom capability, to capture images of the camp from a safe distance in both the visible spectrum and infrared. This distant approach minimizes the risk of detection and allows for a safe retreat if detected. Summers waits until nightfall to acquire infrared images, aiming to detect heat signatures from the camp's equipment. His chameleon and infrared camouflage suit, combined with the vision capabilities of enemy lookouts and snipers, ensures he remains unseen. The images are transmitted to his superiors in real time, who request additional zoomed-in views of specific areas of the camp. Unlike Rombolus, who had to retreat under enemy fire and inadvertently alert the enemy to their reconnaissance, Simmons' mission goes smoothly. He and his squad remain effectively invisible to the enemy, successfully completing our operation. We hope you've enjoyed this deep dive into the captivating universe on Metamaterials on Enigma Universe. These extraordinary substances challenge the boundaries of what's possible in the world of material science, and their potential applications are as vast as the cosmos itself. We extend our gratitude to you, our curious and passionate viewers, for joining us on this enlightening journey. As we continue to explore the enigmas of the universe, remember that the intersection of science and imagination knows no bounds, and the mysteries of the cosmos are waiting to be unraveled. Stay tuned for more captivating content. And until then, keep pondering the wonders of the Enigma Universe. Thank you for watching.